What is Mathematics? Written by Richard Courant and Herbert Robbins. Introduction. The Wonder Beneath the Symbols. Mathematics begins not with numbers, but with curiosity. It asks how things fit together, what patterns lie beneath the surface, and how certainty can emerge from abstraction. Far from being a mere technical discipline, it represents a uniquely human form of reasoning, a bridge between logic and imagination. At its heart, mathematics is an exploration of structure, relationship, and order. It operates in symbols, but its insights go beyond them. Equations, diagrams, and formulas are only tools for expressing deeper truths. What appears cryptic on the surface often conceals surprising elegance underneath. Throughout history, mathematical thinking has allowed humans to navigate the stars, understand the motion of bodies, and describe the shapes of space and time. Its reach extends from the subatomic to the cosmic. Yet its most essential questions remain philosophical. What is a number? What does it mean to prove something? Can infinity be measured? Answering these questions doesn't require technical mastery. It requires a willingness to think clearly and follow ideas to their natural conclusion. With each discovery comes not just knowledge, but a new way of seeing the world. Chapter 1. Numbers that Speak. The journey of mathematics begins with numbers, not just as tools for counting, but as objects of deep inquiry. Natural numbers are familiar from childhood, but they soon give way to broader landscapes. 0, once controversial, now defines absence and anchors entire systems. Negative numbers make sense of debt, direction, and reversal. Rational numbers fill in the gaps, while irrational ones break expectations with their endless, non-repeating decimal tails. The ancient Greeks encountered shock when discovering that the square root of 2 could not be expressed as a ratio. This realization broke the neat harmony of whole number mathematics and forced a leap toward abstraction. Real numbers eventually emerged as a complete continuum, capturing all measurable quantities, whether simple or complex. Even within this expanded world, mystery lingers. Prime numbers, those indivisible by any number but one and themselves, remain unpredictable despite centuries of study. Their distribution seems irregular, yet not random. They stand like pillars in the landscape of number theory, hinting at patterns still beyond grasp. Numbers carry more than arithmetic utility. They embody structure and provoke philosophical reflection. They are invented, not discovered. Yet they describe the real world with uncanny precision. Through them, logic finds a language, and patterns become visible. Chapter 2. The Shape of Space. Geometry is the study of space, how it can be divided, measured, and transformed. It began with drawing lines and angles in sand, but evolved into a rigorous system of reasoning that redefined how space is understood. Euclidean geometry, built from 5 postulates, ruled for over 2 millennia. With it came the notion of parallel lines, the Pythagorean theorem, and the belief that space was flat and absolute. But the 5th postulate, the one about parallels, resisted derivation from the others. Attempts to prove it led to an unexpected realization. There could be entirely consistent geometries where the postulate fails. The birth of non-Euclidean geometry transformed mathematics. In these geometries, space can curve. Lines that appear parallel may converge or diverge. The angles of a triangle may sum to more or less than 180 degrees. These ideas found real-world application in Einstein's theory of general relativity, which showed that mass and energy warp the geometry of space-time itself. Geometry isn't static, it evolves. Coordinates introduced by Descartes fused algebra and geometry, allowing shapes to be described by equations. This shift made it possible to model motion, draw curves, and express dynamic systems. From the simplest triangle to the curvature of the universe, geometry bridges the visual and the logical, the intuitive and the abstract. Chapter 3. The Language of Proof. Mathematics distinguishes itself by its insistence on proof. While science gathers evidence and draws conclusions, mathematics demands certainty. A theorem is not accepted until it is proven, until every step follows unambiguously from agreed-upon foundations. Axioms serve as those foundations. They are statements accepted without proof, forming the bedrock on which systems are built. From these, all further truths are derived. Euclid's Elements was the first great demonstration of this method, but the idea has since been extended to every branch of mathematics. Proofs come in many forms: algebraic manipulations, geometric constructions, indirect arguments, contradictions, but all serve the same goal: to show that something must be true, not just that it appears to be. The pursuit of proof leads not only to clarity, but to creativity. Multiple proofs of the same result can reveal different perspectives, hidden structures, or surprising connections. The Pythagorean theorem alone has been proven in hundreds of ways, each illuminating a different path through the forest of logic. Yet even within rigorous systems, limits exist. Gödel's incompleteness theorems revealed that in any sufficiently powerful system, there are truths that cannot be proven within that system. Certainty, though central, has boundaries, and understanding those boundaries becomes part of the pursuit itself. Chapter 4. Infinity and the Power of Limits. Infinity is not just large, it is a category beyond all counting. Grasping it requires more than imagination, it demands careful reasoning. Some infinities are greater than others, some are countable, others not. And some ideas that seem paradoxical at first become clear when infinity is handled with precision. The notion of a limit allows mathematics to make sense of infinite processes. A sequence may never reach a final value, but it can approach one indefinitely. This idea makes it possible to define continuity, convergence, and instantaneous change. Zeno's paradoxes, like the tale of Achilles and the tortoise, once challenged the possibility of motion itself. How could something reach a goal if it first had to cover half the distance, then half of the remainder, and so on forever? The resolution lies in the concept of limits, the insight that an infinite sum can converge to a finite quantity. With this tool in hand, mathematics entered a new era. Calculus emerged, revealing how curves bend, how velocities change, how areas accumulate under curves. The infinite became not a barrier, but a bridge to understanding motion, growth, and change in a world where nothing stands still. Chapter 5. Calculus, the Mathematics of Change. Change is everywhere. Objects accelerate, populations grow, temperatures fluctuate. Capturing that change with precision requires more than observation. It requires calculus. This mathematical framework allows for the study of how quantities vary continuously, whether in time, space, or structure. Differentiation quantifies how fast something changes. It captures the rate at which position becomes speed, or cost becomes marginal price. Integration, on the other hand, measures accumulation. It finds areas under curves, total growth over time, or the net effect of countless small changes. At the heart of both lies the limit, a way to examine behavior as one quantity shrinks to zero. The derivative arises from taking smaller and smaller intervals, while the integral sums infinitely many infinitesimal parts. The fundamental theorem of calculus connects these two ideas. It shows that differentiation and integration are inverse operations, two sides of the same process. This unification allowed mathematics to model everything from planetary motion to sound waves, from fluid dynamics to electrical circuits. Calculus didn't just enhance mathematics, it revolutionized physics, engineering, and economics. It made the invisible visible, the dynamic predictable. It provided a toolkit for exploring any system governed by change. Chapter 6: Structures, Patterns, and Abstraction. Beyond numbers and functions lies a deeper level of mathematics, one concerned with structure itself. Algebra abstracts operations like addition and multiplication into systems called groups, rings, and fields. These structures capture the essence of symmetry, transformation, and consistency. A group might describe the set of ways an object can be rotated or reflected without changing its identity. A field might define how quantities can be added, subtracted, multiplied, and divided while preserving certain rules. These abstract systems appear across mathematics and physics, linking seemingly unrelated domains through shared structure. Patterns emerge not just in numbers, but in operations. Mathematics finds unity by stripping away the particulars and focusing on form. The abstraction might seem distant from practical concerns, but it is this very generality that gives it power. Once a structure is understood, it can be applied wherever that same pattern arises. This level of abstraction also invites aesthetics. Elegant proofs, surprising equivalences, or symmetries that resonate with visual or auditory harmony evoke a kind of beauty unique to mathematics. It is a world of pure thought, yet its consequences are tangible. Chapter 7: Mathematics and the Physical World. Mathematics and the universe seem uncannily aligned. Equations describe falling objects, predict planetary paths, and model the behavior of gases, fluids, and fields. The language of mathematics fits the structure of physical reality with astonishing accuracy. Wave functions describe the probabilities in quantum mechanics. Geometric symmetries define the particles in the Standard Model. Statistical distributions appear in biological populations, economic systems, and thermodynamic ensembles. From the motion of electrons to the expansion of galaxies, patterns are not only observed, they are expressed mathematically. But this relationship goes deeper than description. Mathematics sometimes predicts phenomena before they are observed. Maxwell's equations predicted electromagnetic waves before radio waves were discovered. Dirac's equations suggested the existence of antimatter before it was found in nature. In many cases, the math sees further than the eye. This mysterious correspondence has led to philosophical reflection. Is mathematics invented or discovered? Why does the universe follow mathematical laws? While definitive answers remain elusive, the success of mathematical modeling underscores its status as one of the most powerful tools for understanding reality. Conclusion: Thinking mathematically. Mathematics is more than a subject. It is a way of thinking. It teaches clarity, discipline, and creativity. It builds intuition alongside logic and invites curiosity while demanding rigor. The patterns it uncovers, the structures it reveals, and the questions it poses extend far beyond the classroom or the lab. Its ideas challenge the mind to work patiently and persistently. They reward deep attention and punish careless shortcuts. Yet they offer a kind of mental liberation, the joy of insight, the satisfaction of resolution, the wonder of discovering harmony beneath complexity. Mathematical thinking sharpens not only the intellect, but the character. It cultivates humility, recognizing the limits of knowledge, as well as confidence in reason. It demands honesty, precision, and patience. In a world full of uncertainty, it provides a framework for finding what is knowable and trusting what is provable. To engage with mathematics is to enter into a tradition of human inquiry stretching back millennia. It is to join a quiet conversation with minds across time, all seeking the same thing: clarity amid confusion, truth beneath surface, and structure within chaos. Thanks for listening.
Did you enjoy this book summary? Got ideas on how we can make it even better? Drop us a quick note. We're always listening and learning from you.